Does that look right?
Yeah.
Yes. All right, well, here's a candy. Good shot.
Oh, you got zoom in.
Nice zoom thing, yeah.
Oh, there's the expert.
All right, well, let's hope that it's actually working.
Do you want to do it?
Oh, yeah, could Lady Ma, could you please take a look and make sure that it's being done correctly? Because you have a lot of experience
It's working.
working. Okay. All right, so let me first review what we were talking about last time because it's so important. And all right, so the idea is if you have something like this, and let this be, say, a unitary transformation that's then dependent upon space-time. And in the jargon, the term that we use to confuse the chemists is we call it a local transformation. And what one does is one replaces d mu by something called big D mu, which is a derivative plus something that some people call a connection. And so what we have then is this d mu on psi I of x. This is a derivative plus a mu ij psi j of x, and of course a mu in general depends upon x. And to make this even more explicit, it's the identity matrix times d mu plus a mu, which is a matrix, ij psi j of x. All right. Now, how do we make this work? Well, we make this work by having d mu transform in such a way that it absorbs the u that psi gets. So in other words, we want d prime mu to be u d mu, u inverse or u adjoint. And that means that we have d mu plus a mu prime equal to u d mu plus a mu u inverse. And now d mu acting on u mu inverse, it first of all goes through it and multiplied by u inverse, which is just the identity. And then what's left is u a mu u inverse plus u d mu u inverse. Okay? So there are three terms here. There's the d mu, in other words, u d mu u inverse is u d mu u inverse by itself plus u inverse d mu, and that's simply u d mu u inverse plus d mu. Okay. All right. And that tells us what our relation is, how this matrix A mu has to transform, namely A prime mu of x has to be u of x, a mu of x, u inverse of x, plus d mu, oops, mistake, plus u d mu u inverse. Okay? And this derivation is a little bit shorter than the one I did for you last time, so I like it a little bit better. Also, it gives us a somewhat nicer form, u d mu u inverse, rather than d mu u inverse u, which requires all these extra parentheses. Okay, now of course f mu nu, the matrix, is the commutator of d mu with d nu, and so f prime mu nu, we saw this last time, is u d mu d nu u inverse, which is of course u f mu nu u inverse, and so we can make something that's an invariant action by taking the trace. So trace of f mu nu both primed is trace of u f mu nu u inverse u f mu nu u inverse, and this of course is just trace of f mu nu because that they cancel and you can bring this one over here because it's a trace. All right. Okay, so those are the basic ideas of Yang-Mills theory. That's really all you need to know. And if some of you have a hot date, you could just leave, and I'll just go on by myself. So this then is the action for the gauge field, the action of a mu, in other words. And for fermions, well, if we use Weinberg's notation, it's gamma mu d mu plus m psi, where this, what we mean here is this is a column, this is a row vector. Anyway, in other words, ij, this is the identity ij, j, summed over ij. So this is invariant because if the transformation is unitary, u dagger u is invariant, and then psi bar gamma mu d mu psi prime is psi bar u inverse, or u adjoint, which is the same as u inverse if we're talking unitary groups here. And then this is u d mu u inverse u psi. And so this is psi bar d slash psi, to use a Feynman's nice notation. Just cancel it when I take. For scalar bosons, you do something similar. You say d mu phi adjoint d mu phi, whereas now this thing is a column vector. So in other words, this is ijj I, K, K, so it's like that. All right. I lost my reading glasses, so I'm having a little trouble here with this. Maybe I should ask one of you to. Now, if psi or phi or whatever has goes from psi 1 up to psi, let us say, what did I call it? Little n. If that's how many fermion fields we have, then in the covariant derivative here, this thing here has to be an n by n matrix. In fact, I could have stayed here. In other words, this thing is this is psi bar d slash plus a mu slash psi. So this has to be an n by n matrix. On the other hand, if phi has m components, then when we do d mu plus A mu, this has to be an M by M matrix. So we're going to have different sized matrices. Now let's see. Let me review something about the basics of Lie groups. This is something I do when I teach the group theory, the second semester of course of math methods. But what we've got is, let us say, a group, and we have some parameterization of the group with some parameters alpha. For SU2, there would be 3 alphas. For SU3, there would be 8 alphas. For an arbitrary group, it's whatever it is. And in general, these could be, this could be a compact or non-compact group for the moment. Of course, if you have unitary representations, then you're strictly compact. Okay. Now, what is a representation? Well, it's a map from the group to some matrices, say n by n matrices with the same parameters. Okay. And now, what's true about a Lie group is that the group elements depend upon the parameters in a continuous way so that you can actually differentiate, and you can say, in fact, that you can define something called a generator as minus I, the derivative of d of alpha, say, with respect to alpha sub A, where all the alphas are 0. So, and the idea here is that d of alpha, the small alpha, is the identity plus I alpha A T A summed over whatever these A's happen to be. In other words, d of alpha is e to the I alpha A T A. And when the alphas are really small, you can expand this way. Again, when you take the derivative, you're at alpha equals 0, you're talking about small alphas, and then the i's cancel, and you get the generators by differentiating that. Now, we can see if we have an expression like this, and we take the adjoint of that, the alpha adjoint, well, this will be e to the minus I alpha A. Oh, the alphas typically are real. Whether you're talking compact or non-compact, at least in my book, I take the parameters real. Well, in my book, I was using the English expression, but also in my book. In fact, in my book, I forgot to say these parameters. I just treated them as real. Anyway, minus I, this would be then TA dagger. And if we want this to be D, the inverse, well, the inverse of alpha, of course, is e to the minus I alpha A TA. I'm summing over A using the summation convention. Okay, so if the representation is unitary, then the generators have to be Hermitian. So TA dagger equals TA is equivalent to D of alpha dagger equals D inverse. Okay. And so we have lots of Lie groups. Some of them have unitary representations. If the representation is unitary, then these generators are Hermitian. If the generators aren't Hermitian, then the representation isn't Hermitian. And you can see what happens if you have d of alpha equal to an exponential like this. The t's being real, t's being Hermitian is like they're being real. Okay. In fact, you can imagine taking one of these guys to be completely diagonal. Then if it's Hermitian, this is a bunch of real numbers on the diagonal. And then this thing is obviously a unitary matrix, in fact, a diagonal unitary matrix. On the other hand, if these aren't Hermitian and you diagonalize them, then you've got some complex numbers, or in fact what you usually do is you take the generators of an arbitrary Lie group, you separate them into Hermitian and anti-Hermitian generators. The anti-Hermitian generators are simply I times a Hermitian generator, and so these guys would have, if they're diagonal, that means they have imaginary numbers on their diagonal, and that means this thing is a real matrix. You let the alphas go to infinity, this thing takes off. We could say it inflates. That then is a non-compact group. Non-compact groups are ones in which the representations are not unitary, but instead the matrices can get arbitrarily large. Okay. All right, now, if we take these generators, we can define an inner product on them. And the inner product, a natural inner product, is the trace of TA, TB dagger. We can call this the inner product of, let us say, TB with TA. And, you know, whenever you define an inner product, you can use the Gram-Schmidt process or some other process to make these things orthogonal. And so what one can do is make them orthogonal. That is to say, we make a linear transformation of the TAs to so that they're orthogonal. Now you say, well, we ought to make them orthonormal, but it turns out that you, how shall I say, you can't make them orthonormal in general. Now, we'll see why in just a minute or two. All right, well, the idea, let's consider a particular representation with generators little ta, and consider this product e to the I epsilon tb, e to the I epsilon ta, e to the minus I epsilon tb, e to the minus I epsilon ta. And now, if you expand these guys up to powers of epsilon squared, multiply them together, cancel everything, after 3 or 4 hours you find that, in fact, this is the same thing as e to the epsilon squared, the commutator of TA with TB. Whenever I say TB, I think of the disease. And in fact, there was a rather amusing play written by, who's that marvelous comedian? He always plays the role of a New York Jew, and
Woody Allen.
Woody Allen, yeah. Well, Woody Allen wrote a marvelous play, I forget the name of it, but part of the play, at least, takes place in ancient Greece. And so there are various characters, and let's see, one of the characters might be tuberculosis, and another one, God, I should have rehearsed this before I started. But if you think of the names of the diseases, many of them are Greek names. And he has these marvelous conversations between these different ancient Greeks dressed in white robes, of course, and they each one has a name of a disease. All right. Okay, now, what about these TAs and TBs? Well, the idea is that if you take these are matrices that are representing the group, right? And consequently, then, this thing has to be of the form e to the epsilon squared some linear combination, I, F, CAB, TC. It has to be a linear combination of generators because group multiplication is closed. So this is in the group, that's in the group, the whole product has to be in the group, and in particular the representation, if it has to be faithful. So, all right, so what we have then is that for this representation at least, TATB is I, FCAB, TC, and I've used an upper index because I'm considering non-compact as well as compact for the moment. But when the representation is compact, this index gets very heavy and it falls down around there. All right, now let's suppose we have another representation. Well, the other representation would be EVI epsilon TB, EVI epsilon TA is minus I epsilon TB minus I epsilon TA. And this also has to be e to the I epsilon squared TC, and it has to be some linear combination, but in fact it has to be the same linear combination, and the reason is that this is representing the group element in which all the parameters are 0 except for the bth one, and the bth one is epsilon. This represents the group element that corresponding to all the parameters 0 except for the 8th element, which is then epsilon. And the same thing is true here. That means this guy has to represent the same group element as that guy. And the only way it can is if the parameters are the same. So in other words, the FCAB, which are the structure constants, have to be the same for the TAs as for the little TAs. Okay, that's basically the idea. The structure constants are representation independent, and the reason is that the representations represent the group multiplication, and we've adopted this exponential parametrization of everything. So these then are the structure constants, and they're the same because, for example, in the representation big T, epsilon squared FCAB has to, well, yeah, right. That is the, right, that's the C element. The C element, when you have this particular product of the D's, and this thing has to point to the same group element, G of epsilon squared of CAB, which points to the D little t epsilon squared of CAB. Okay, so what do we have? What we have is this.
So I actually have a question.
What's that? Excuse me?
I have a question.
Yes.
So the structure constants are the same, but the order in which they appear in our linear combination is going to be completely dependent on whatever
I didn't quite understand. The structure constants are the same in all representations.
Right. But like we want to write out that full linear combination FCAB, capital TC, for example. So you have a term with one of the T's, another T, another T. And the full set of structure constants is the same regardless of which representation you have, but like which generator they correspond to may be different. For example, if you have an ordering of your generators
Yeah,
for one representation and ordering of your generators for the other, the structure constants are going to fall in a different order for the linear combination.
yeah, I guess so.
I don't know if that's even useful.
No, I think what you're saying not only makes sense, but it's, yeah, right, but, you know, so as not to make things arbitrarily confusing, we'll choose the same order of generators in every case. Yeah, okay. All right, so this is basically the definition of the structure constants in all cases. And what we notice then is that we can take a trace of that expression. And if we do, we get the trace then of TA with TB. T dagger, let us use D. Then that's I FCAB, because of this, trace TC TD dagger. But we've done the Hilbert-Schmidt thing on this, so this is equal to I, what is it? I over IK, sorry. IK FCAB delta CD, which is to say IK FD AB. So this trace is the structure constant together with this constant that's characteristic of the representation, I guess. Okay, so then what we can do is we have a formula here then for the structure constants, namely that we can say FCAB is equal to minus I over K trace of TATB TC dagger. And so that's a general formula for compact or non-compact groups. Okay, now notice that if instead we write down BA, then this is minus I over K trace commutated here TBTA TC dagger. On the other hand, that's the same thing as I over K trace TATB TC dagger, which is to say minus F A B C. So what that tells us is that in general the structure constants are antisymmetric in the lower indices.
De Blasio rule.
What?
The de Blasio rule.
De Blasio? Yes, yes,
Right.
yes. Like the mayor of New York. Yes, I think of her every time I try to write something on the board, but I just hate writing in English. Or it's even worse. Okay. So whether it's compact or non-compact, the structure constants are antisymmetric in the lower indices. Now, what about if they're unitary? Well, if they're unitary, then this dagger, then if the representation, if the representation is unitary, then all the generators are Hermitian. And then what we've got is that this is actually minus I over K trace of TATB TC. And so let me skip to where I actually worked this out. And now let's consider what FB AC would be. Then that would be minus I over K trace of TA TC TB. No adjoint because it's a unitary representation and the generators are Hermitian. But then this is minus I over K trace TA TC TB minus TC TA TB. Yeah, right. So this is not doing anything. This is just expanding that. And then what we can do is we can say, well, this is minus I over K trace, and we can move the B forward. Trace TB, TA, TC, minus, and now we move the C backward. We get TA, TB, TC. Well, now we see that this is minus I over K trace of TBTA with TC, which is just FCBA. But FCBA we know is minus FCAB. And what we started out with was FBAC. That's an F, not a minus sign. So now what do we see? We see that the structure constants are antisymmetric in these two indices if the group is compact, has Hermitian generators. Well, in that case, it's antisymmetric in all, because if you only have three and you have double antisymmetry, then everything's antisymmetric. And so what we can say is that for unitary groups, or unitary reps, by the way, a representation is a map from the group to matrices. Each element of the group goes to, well, it's a map, it goes to a single matrix, and its space, it represents the group law of multiplication faithfully. In other words, if G1, G2 is G3, then D of G1, D of G2 is D of G3. And that's what I use to say the structure constant score is the same. Okay, so let's see, where was I going with this? For unitary representations, then, the structure constants are totally antisymmetric. And so we can say FCAB, we'll just write that as FABC. We'll just drop the last index, the upper index, put it in the end. And then we say they're totally antisymmetric. Totally antisymmetric if the representations are uniform. Now, in fact, in this case, they're also real. And in order to see that, let's just write FABC is what? Well, it's minus I over K trace TATB TC. And so if we take the complex conjugate, we get F star ABC is I over K trace of, well, TC dagger, TB dagger, TA dagger commutator, but we're talking unitary representations, all the generators are Hermitian, so this is I over K trace TC, TB, TA, which is the same thing as minus I over K, trace TA, TB, TC. I've done a double flip here. Namely, you can move this to the end, no problem, and you interchange those two, and you get a minus sign. But this is what we've seen was FABC. So all the structure constants are real. So the structures are, so for unitary reps, FABC, totally antisymmetric and real. So that's very nice. For the group SU2, these structure constants are very simple, namely FABC is just epsilon ABC. It's the Levi-Chivita totally antisymmetric. It's very simple. And in fact, it would, I guess, if you're going to be totally antisymmetric, I'm just wondering. Anyway, I don't know quite where to go with that, so I'll just leave it there. And what we have here is sigma A over 2, sigma B over 2 is I epsilon ABC, sigma C over 2. So that's the thing for SU2. For SU3, it's, we still have structure constants, but they're more complicated. There are 8 generators. And this is called the fundamental representation. It's also called the defining representation. And in fact, that's the term that Howard Georgi, his book, uses. Georgi's book, I think, is the best one on group theory. The only problem with that group is that he kind of assumes the reader is as smart as he is, and which is also one of the problems with Weinberg's books. So you sometimes wind up being a bit puzzled with Georgi's book. On the other hand, they're very good books. They're the best books as far as I'm concerned. Okay, so the Jacobi identity. This is really worth knowing about, and I'm sure you already know about it. But let's just see it again because it is so important. So that's the commutator of A with BC, and we can rewrite it as ABC minus BAC plus BAC minus BCA. These are probably all ticker symbols on the New York Stock Exchange, or at least on the NASDAQ. And now you see, in fact, this thing is AB C plus B AC. All right, so let me call this 1. And you could also interchange B and C, and then you get the rule A commutator CB is A with C commutator times B plus C commutator A with B, and I call that 2. And then 1 minus 2 gives this. In other words, if you subtract this from that, well, you basically have a double commutator. You have A with the commutator of B with C. And now subtracting, you see there's some cancellation. So the first one here is AB plus back. God, well, never mind the cancellation. What you get, oh yes, what you get, you see, is there's a commutator. This is the commutator of, let's do this one. There's the commutator of AB with C, if you subtract this one. So this is the commutator of AB with C, and then the other term is the commutator of B with the commutator of AC. So that's one form of the Jacobi identity, and in a sense it's the only form because they're all equivalent to that. But that's the one that falls out neatly. And now there's a remarkable consequence of that. Namely, if we rewrite it in terms of the generators, then I'm a little worried about the time because I'm using a blackboard space like nobody's business here. I guess I'll have to write really small. Okay, so let's do this. TA, TB, TC. So I'm going to just rewrite the Jacobi identity. And what you normally do with the Jacobi identity is you pull everybody to the one side and then have an equation to form something equals 0. Okay, that turns out to be TB, TCTA plus TC TATB equals 0. All right. Now, okay, I forgot to say that I'm going to make a definition now. I'm going to make a definition of a certain matrix, TB, and the AC matrix element, I'm going to say is IFCAB. So this is a definition then that works for compact and non-compact groups. So in other words, I'm going to take the structure constants and make a definition. And because these structure constants are given by this rule over here, namely FCAB is minus I that, and so I times minus I would be 1 over K trace 1 over K trace TATB TC dagger. So that's the definition I'm going to make for an arbitrary group. All right. With that definition, and a great deal of care and checking of indices. This is, I do this in my book explicitly, but I think I'll skip some of the tedium for you. What you get is that this term is minus FD BC FE AD TE. In other words, this guy here is going to be the structure constants. Maybe I should do one of them. Okay, so let's do TA, TB, TC. TA, TB, TC. So this is TA, I, F, B, C, D, say, T, D. Then A with D is an extra I, so a minus sign. F, the lower part is AD, E, TE. And then, of course, it also has FD, BC. And there it is, minus FDBC FEAD TE. Okay? All right? So in other words, Jacobi identity gives us these double commutators. We use the structure constants. We express this in terms of the structure constants like this. TBTC is that. And then TA with TD, again structure constants. The i's give you a minus sign, and you get that. All right. The same thing is true with this one. It gives you another term, which is FD CA FE BD TE. And this one gives us minus FD AB FECD TE equals 0. Okay. And now, what can we do? Actually, I was premature. Now is the time to make this definition. Okay, for some reason. Okay, now these TEs, of course, are orthogonal. We made them orthogonal. And so we can, this matrix equation implies, in particular, that FDBC FEAD plus FDCA FEBD plus FDAB FECD equals 0. Now we make this definition. In terms of the F's, we're defining these matrices. And what do we find? What we find is that this whole equation can be rewritten as minus TB TA CE plus TA TB CE minus IF DAB TD CE equals 0. Now, that, I mean, what we could do is I could maybe go through one of these. All right, let me just show you how this one works. Well, this one here, FDBC is minus FDCB. Oh, wait a minute, I don't want, I want, I think I want to do it the other way. Let me, yeah, that's right. Okay, hold on, let me get in. Of course, I've got my footnotes here. I'm going to just sort of grab it so as to not. Well, it's probably better to do it directly. All right, so this thing, by the way, when I said this, I think, right, okay. So let's use that definition there. Then what is this saying? TB, so this is minus TB, let us say CD, TA, DE. That's what we want, okay? Now, TB, CD is, let's hold the minus sign. TB, CD is IFD and C, and then the other one has to be B, I guess, right? Right. And then this one is an I, F, and now the A index has to go to the second one. So the A goes there. And this is the eth element. The eth element is there. And then the other one must be D, right? Okay. So there is, that's what we're talking about. And so that should be the same as this. And indeed, the I times minus I is a plus, and I've got the CB backwards and the DA backwards. Flip them both and you get this. Okay, so it's the same. Carrying this out is a little bit like weaving a Chinese rug. Okay, so okay, so what have we found out here? What we found out is that these matrices that we define satisfy this relation. Or getting rid of, or in matrix notation, TA, TB is I, F, A, B, C, TC. In other words, the matrices that I defined in terms of the structure constants in this way, because of the Jacobi identity, these matrices obey the commutation relations of the group with the same structure constants. And this is a particular representation, and this is called the adjoint representation. So the structure constants define for you the matrices. Maybe turn the camera a little bit so they can see. The structure constants define the matrices of the generators of the adjoint representation of the group. And for SU2, these adjoint representation matrices are the ordinary rotation matrices of the rotation group, the 3x3 matrices of the rotation. Let's see what else we have. Okay, now there's some cute thing. I think that what we've done so far is the main. I've done the important ideas, I think, about Yang-Mills theory and Lie group, the theory of Lie groups, usually more. But now I'm going to do some things that are more technical and less important, and they're kind of details. Okay. One of them is, if we take the generators and we sum those generators, well, this turns out to be something called C2, C for Casimir, 2 for, I don't know what the hell 2 is for. I guess it's quadratic, so I guess that's, times the identity matrix. So these are n by n matrices, the n by n identity matrix. Now, why is this true? Well, if you take the commutator of the sum, TA with, say, TB, what do you get? Well, you get TA, TB minus TA, TA, plus TA, TB, TA, minus TB, TA, TA. Okay, so the basic thing, commutator on the left is this minus that, and in between I stuck, in between I made a mistake. So let me, yeah, this is AB. I put in TA, TB, TA, and subtracted and added TA, TB, TA. Okay. So what is this? This then is TA times the commutator of TA with TB plus the commutator of TA with TB times TA. And now we're in unitary representations, okay? So we're compact groups now. This doesn't work. This thing isn't a Casimir in general. This then is TAI. In fact, I can do it in general, and I'll show you that it's not a Casimir, you see. Not invariant. This thing is IFCAB TC. And so what do we have? What we have here is IFCAB times TATC plus TCTA. Well, this is symmetric, obviously. And if the group is compact, it's antisymmetric in these two indices. Otherwise, it isn't. And so this is 0 for unitary reps. And that's called. So what does that say? First of all, I haven't really finished. What I've said here is that every generator for compact representations, or for unitary representations, every generator commutes with the sum over all the generators. Now, you can be sure that this then is a multiple of the identity because of Schur's lemma. I can't spell Schur. If I look in my notes, I think I see it. SCHUR. Schur's lemma, there are two parts to it, but the bottom line, the take-home message is, if something commutes with every element, every generator of a group, then it's got to be a multiple of the identity matrix. Maybe I should go back. I proved Schur's lemma in this book. Let me just give it to you in two parts because I think that Schur's lemma is something that is pretty important, and so it's good to have maybe a real statement of it as opposed to just something that I throw out on the fly. So this is section, if you want to look in my book, it's section 10.7. And it says if D1 and D2 are inequivalent, irreducible reps of a group G, and I better explain all these terms, and if D1 of G, A, is A, D2 of G, for some matrix A, and all G in the group, then A is 0. So that's So you have a representation in terms of square matrices. Two representations can be equivalent if D is equal to, say, S D prime S inverse, where S is non-singular, obviously, because this is an S inverse. So these are equivalent. So inequivalent means not that. Reducible, if you can take the representation and you can write it in some block diagonal form, then it's reducible. If you can't, it's irreducible. There are fancier definitions, but this is the one that tends to stick to one's neurons, at least if one is a physicist. Okay, so this says then if you've got two inequivalent irreducible representations and some matrix commutes, it's kind of a funny commutation. It's not really commutation because these are different representations. But if you have this, A has to be 0. Okay, what's part 2? Part 2 is if you have, oh, by the way, I think I had to say finite dimensional. Well, presumably this is finite dimensional. We're talking representations and so forth. All right, so we have a finite dimensional irreducible rep D of G, and D of G A is A D of G. So now we've got that, in other words, the commutator of D of G with A vanishes for all G in the group. Then A is some number times the identity matrix. And so it's really part 2 of Schur's lemma that we're applying here. And as I say, the proof is there. It's not the most obvious thing in the world, the proof of Schur's lemma. That, I think, is why you will hear it referred to many times in many books, but not proven in most cases. Let's see if I can go on to other topics. Okay, so we were saying over here that, remember, for compact groups, we have trace of TATB is delta AB, that's delta AB. In general, it was TB dagger, but for compact groups, it's just that. And this K here is something that Schwartz calls T of the representation, delta AB. And he also calls it C of R, delta AB. Now, those are several different terms, and he calls it, you can call this the index. And for SUN, and if we're talking the fundamental representation, so SUN, we arrange in physics departments that the trace of TATB is a half delta AB. I don't know why we do that, but that's what we do. And I guess it's that we want the generators to be sigma A over 2. Okay, now the fundamental representation for SUN, how many generators do we have? Well, if you think about it, you've got, the thing looks like this, e to the I, alpha A TA, and so this is, you're representing an arbitrary Hermitian matrix, and if it's N by, if it's SUN, and we're in the fundamental representation, then this is an n by n matrix. So we're wondering how big, how many generators do we need to make this? Well, if you wanted to make an arbitrary Hermitian matrix here, you'd need n squared, because you would want to have well, along the diagonal, one of them could be 1, 0, 0, 0, zeros everywhere else. And then you could have, say, a 1 here and zeros everywhere else. Okay? But these aren't really Hermitian. If you make them Hermitian, then what you do is well, on the diagonal, you can just do what I did. But if you're off diagonal, you have two possibilities. You can have 1, 1, or you can have 0, I minus I, 0. So you actually have two. And so what this means effectively is that to a first approximation, you need n squared of them. But there's one that you don't want because we're talking SUN. The determinant has to be 1. And the determinant of a matrix like this is actually the logarithm of the trace of the logarithm. And so if we want that, the trace of logarithm, we want that to be 0, that trace, all these things have to be traceless. And so that means that the one that has the same element throughout the diagonal, that has to vanish. In other words, the sum of the diagonal elements has to be 0 for any of the generators. And so you can't really have, for example, if it were 2 by 2, you can't have 1, 0 and 0, 1 because both of these have trace 1. So what you have to do is you have 0 minus 1, and that's it. That's the traceless one. So there are n squared minus 1 generators for SUN period. That's the number of generators. For SU3, Gell-Mann introduced some matrices called lambda A, and then we stuck in a 1/2 and called them TA to be 1/2 lambda A. And in general for SUN, so SUN, fundamental or defining is a better word than fundamental. So the defining representation, SU2, they're 2 by 2 unitary matrices. SU3, 3 by 3 defining. And that's the correct terminology. That's what Georgia uses. Well, in that case, what we have is TATB is 1 over 2 capital N delta AB plus 1/2. This is a pretty remarkable relation. I don't really know how to derive it. But anyway, we have a 1/2 D ABC TC plus 1/2 I FABC TC. Okay, so that gives us, well, you can see where this sort of comes from. The trace relation together with the index being a 1/2 gives you the first term. The structure constant relation gives you the third term. And then what's left over, well, whatever it is, it has to be, I think this is totally symmetric, the DABC. And that gives you that. And yeah, it is totally symmetric. You can write DABC the following way. Twice the trace of TA with the anti-commutator of TB with TC. And so this is obviously totally antisymmetric. SU2 is somewhat simpler. It has D equals 0. And that's just the rule. Sigma A over 2, sigma B over 2. Well, it's delta AB over 4. because sigma A squared is 1. And then it's plus a half I epsilon ABC sigma C over 2. And multiplying through by 4, what we get is sigma A sigma B is delta AB plus I epsilon ABC sigma C. This is the thing that you want to write down somewhere for Pauli matrices. Okay, well, we're over time, so let me just say time out here. And are there any questions? By the way, did somebody ask a question and not get a candy? Oh, Jesus.
Not me.
All right, anybody else ask a question? All right, you should ask more questions because these are confusing matters. And I think you've learned more if you ask questions because it's more natural psychological involvement. Okay? We evolved language to communicate with each other. It has a survival value, even for graduate students. You should use it when you're in class. Yes, a question. Whoa!
This middle
All right, swing the camera around. So.
I don't quite see how you go from the commutator to the FBC.
How I went from there to there?
No, the one before that one.
From there to there?
Yes.
Oh, the commutator of TB with TC is IFBC TD summed with this D there. That's the fundamental relation. In other words, the fundamental relation here is TB/TC is IFBCD TD. And that got us to there. All right, let's look over here. Swing it around. Here. Yeah.
Oh. Alright.
Yeah, this
I was
is...
looking at that one.
All right, so this student is either hungry or has a question. Yes.
This FADC is antisymmetric.
In these guys.
In these guys, it can be directly seen from this equation, right?
Yes,
So we
absolutely.
don't need that.
You're right. This is a better way of seeing it. All right, let me give you in fact, let me give you two of them. Oh! Any other questions? All right, I guess we can turn it